Okay, so I'm the last guy between us and dinner, so I'll try to blow through this. First, I need the clicker.
Oh, it's right there.
Okay, let's see. So any presentation you'll ever see by NVIDIA is going to start out with this slide. For the past 30 years, CPUs have been getting predictably more powerful year over year, thanks to mostly thanks to something called Dennard scaling. You might have heard this. It's called Moore's Law. CPU doubles every 2 years. Well, around 2010, this started to slow down. And here we are in 2019, and Moore's Law is effectively dead. The CPU is no longer giving us that same significant performance increase year over year. CPUs aren't getting any faster, so companies like CPFD have to start getting more creative and think outside the box. Luckily, we started putting GPUs in the data center in the mid-2000s, and we have picked up the torch of Moore's Law, and we have sprinted with it. I'm proud to say that we have shattered Moore's Law. We are now accelerating at a rate even faster than Moore's Law because of our huge R&D spend. We are spending lots of money not only optimizing the hardware, but the software as well. NVIDIA is a company of 13,000 employees. 12,000 of those are pure engineers. And the 3 main market drivers that are pushing this R&D spend are artificial intelligence, high-performance computing, and of course, rendering and graphics. So I could try to explain to you, the differences between a CPU computing data serially, one after the other, and a GPU crunching through data in parallel. But I will never be able to do as well as the Mythbusters guys did a couple years ago at our GTC conference. So they're going to show you how a CPU would paint a picture serially, one after the other, and then how a GPU would paint a picture. So if we can go ahead and play this. Hopefully it's got sound. If not, I've seen it a million times, so I can just lip dub over it.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. And let me speed it up.
Speculative execution. It's still very much a serial process, one after the other. And
ladies and gentlemen,
Leonardo 2.0. 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Yeah. So it's a little tongue-in-cheek, but really not by that much. Intel's Skylake CPU has 28 cores. Next generation Cascade Lake has 32 cores. Does anybody know how many cores are in a V100? Dirk? A little more than that. So it's over 5,000. It's over 5,000, very close. And the way that you talk to the GPU, the way that you send your data through all 5,000 of those lanes is with the CUDA programming language. Now, unless you've got a PhD in computer science, you're probably not going to be developing in CUDA because it's really difficult as CPFD is starting to learn. But the good news is you don't have to because we've already done the work for you. CPFD's already done the work for you. You can come here at the application and frameworks layer and take full advantage of that massive parallelism with just minimal effort. So we've got over 600 HPC applications fully accelerated on the GPU. Added to that list recently is CPFD. But we also have NAMD for molecular dynamics, Amber, we've got quantum chromodynamics, weather simulation. I come from the oil and gas space, so things like reverse time migration and SpecFem 3D for a seismic wave propagating through. All fully accelerated on the GPU. As well, we have every major deep learning framework fully accelerated. We heard about TensorFlow earlier today. It's by far the most popular. But if you're using PyTorch or MXNet or Chainer, really popular in Japan, these are all fully accelerated on the GPU. Recently, we took a step back and we said, okay, most companies aren't into deep learning yet. They're still on the machine learning side doing things in Python. So we went back and we accelerated the traditional machine learning workloads on the GPU. So if you're using Pandas or sklearn, we now have a platform called Rapids, which is drop and replace. So you write, 2 or 3 lines of code at the top, and instead of sending your data to a pandas data frame, you'll send it to a CUDA data frame. Instead of instantiating an sklearn XGBoost model, you would use a Rapids XGBoost model and get that kind of parallelism just right off the bat. Now, this software stack is all developed on one platform. We call it the Tesla platform. And the good thing about the Tesla platform is it runs everywhere. We don't care if your GPUs are on-prem, in the cloud, or at the edge. If it's developed on this software stack, it will run anywhere. Now, this hyper-focus on both the hardware and the software has led to some insane speed-ups in a really short amount of time. So in 2015, we had the Kepler architecture, K80s, and it would take us 25 days to train a ResNet 50 algorithm. ResNet 50 is a popular computer vision algorithm, 25 days. 2016, we introduced the Pascal architecture and this new technology called NVLink, which allowed us to connect multiple GPUs together with minimal overhead, make them look like one piece of silicon, and we dropped it from 25 days to 20 hours. 1 year later, in 2017, we have the Volta architecture and the famous tensor cores. Now, what a tensor core does is if you've ever had the misfortune of having to multiply matrices by hand, there are 2 steps. You take a column, and you take a row, and then you multiply element-wise, step 1. Step 2 is you sum those up. The magic of tensor cores is that they do the multiplication and the summation in one step. So just a few tensor cores give you really great acceleration. Those 2 technologies dropped us down to 8 hours in 2017. At the end of 2018, there was this contest called MLPerf, and it was a collaboration between NVIDIA, Google, Amazon, Facebook, all the heavy hitters in AI. And we basically came up with the AI Olympics to really just kind of test all of the different hardware that's out there in an unbiased way. It should not surprise you that NVIDIA took home most of the gold medals. So training on a single node, the DGX2, it has 16 V100s fully connected with NVLink. We trained ResNet 50 in just 70 minutes. And then my favorite competition was the at-scale competition. And that's where they said, just throw everything you have at it. What is the absolute fastest you can get a ResNet 50 model trained? We used our Saturn V cluster, and we trained ResNet 50 in 6.3 minutes. So in a matter of 3 years, we went from 25 days to 6.3 minutes. That is the power of GPUs. And the main workhorse behind the DGX1 and 2 is the V100. Not quite 10,000 cores, but it's got over 5,000 CUDA cores, 640 tensor cores. If you're doing high-performance computing in double precision, that'll give you almost 8 teraflops. In single precision, we're looking at almost 16 teraflops. This thing is an absolute workhorse, and you can consume it in several different form factors. So out of curiosity, how many people here still use their compute with like an actual workstation that's under their desk? Raise your hand. Not a lot of people. Okay, and then how many people do you, what was that? There you go. Okay, so that kind of counts. And then how many people have a compute cluster either on-prem or in the cloud? Okay, a couple more people. Well, for the workstation users, we developed the DGX station. And rumor has it that this kind of started as just like a pet project from a couple of our engineers, wondering if they could connect a couple V100s and plug it in under their desk. Well, the answer is yes. The DGX station has 4 V100s connected with NVLink. It's water-cooled, so it's whisper quiet. It plugs in under your desk, and I've seen it in person. That gold plating looks really nice. It's a good-looking box. So this is just, it's the strongest workstation on the planet. The DGX1 is probably our most popular of the group, and it's got 8 of the V100s fully connected. And then the DGX2, as we mentioned, is the world's most powerful single node with 16 fully connected V100s. NVIDIA GPU Cloud is not what you're thinking. It's not like AWS or Azure. It's really our online container repository. So containers have kind of taken the IT world by storm, and for good reason. I mean, they're great. They simplify deployment. You can get started up and running really quickly, and then they're very portable between different compute environments. Well, we saw the popularization of containers, and we decided that we kind of had to put our own green stamp on it. So we came out with NGC containers, NVIDIA GPU Cloud Containers. And what these are fully optimized containers that have been optimized by us. We do a lot of work optimizing these, releasing them on almost a monthly basis, and we put them in NGC for free. So if you're using TensorFlow, PyTorch, maybe one day we'll even be able to get a CPFD container in there. Do not download these frameworks by yourself, because there are a lot of hooks, a lot of dependencies, and if one little hook isn't optimized in the right way, you're not going to get good performance. So if you're using any of those workloads, I highly recommend you check out ngc.nvidia.com and start using our containers, because we do a lot of work optimizing them. For the AI workloads, this is not a joke. I mean, this is for real. For training a ResNet 50 algorithm on CPUs only, you're looking at about 300 CPU-only servers. This will cost you about $3 million. Or, if you want to get the same throughput, you can buy a single DGX2. It's 400 grand around there, so he was right. It's 1/8 the cost, 1/18 the power, as he said. This is 180 kilowatts, and this is only 10 kilowatts, and 1/30th the space. So it's just really an impressive machine. For high-performance computing, the algebra isn't quite as nice, but it's still impressive. So Amber is a very popular HPC application, so is GTC. For Amber, you can buy one GPU node containing 4 V100s and spend about $45K. Or you can buy 74 CPU-only nodes at $9K. The GPU option is going to save you 620 grand. For GTC, very similar. It's going to save you just under 200 grand. Our CEO is famous for saying, when it comes to GPU computing, the more you buy, the more you save. And it really is true. The proof is in the pudding. So there was a Gartner report that came out a couple years ago that said something like 60% of CIOs see infrastructure impeding their AI and HPC development. So we kind of raised our eyebrows and we partnered with every major OEM, every major storage vendor, and we came out with what we call reference architectures. So if you're going to build out your own HPC cluster and do it by hand and kind of whiteboard the architecture, maybe you'll get up and running in 3 months, or you can stand on our shoulders, take from the lessons that we've learned building our own internal cluster, helping dozens of other customers build their clusters, and get up and running in about a week. So this is not just the compute, but this is also the storage, the networking, the switches, everything you need for an optimized cluster. We've answered those questions, and we've published them in our reference architectures for free. CPFD is soon to be offered in the cloud, hopefully. And we are partnered with every major cloud provider. They're actually our biggest customers. We love the cloud vendors. And so if you are using GPUs in the cloud, we want to make sure that you're supported. So we're in every major cloud. Let's look at the important ones, like the P100 on. So at this time, the T4 was only offered in Google Cloud and Baidu. I'm pretty sure it's now offered in AWS. But with CPFD, y'all are going to want the larger memory frame. So you're going to want the V100, which is offered in just about every major cloud, as well as NGC, fully supported on all of those. Just a couple different cloud instances showing that, hey, look, you don't have to do this on-prem. You can go to the cloud and get very impressive speed ups. For NAMD Molecular Dynamics, using 4 V100s, about a 10x speed up. Chromax isn't as impressive, only 5x. Chroma, if you're doing quantum chromodynamics, we're looking at a 60x speed up. And then again, SpecFM 3D for seismic wave propagation, we're looking at about a 67% or 67x speed up. So I know we're running low on time, so I'm just going to kind of quickly go through a couple different customers, what they're using our GPUs for. So NASA is collecting a ton of satellite imagery, and they've gotten to this deluge where they just have so much data they can't process it in real time. So they're partnering with us on their satellite imagery, and we're really helping them utilize and make real-time decisions. Baker Hughes GE has probably the most advanced predictive maintenance solution in the oil and gas market. They're looking at these things called ESPs, electric submersible pumps. Very tricky beasts out there on the rig. And whenever they failed, they took the entire rig down with them. So they had tried in the past to kind of do a predictive maintenance solution using traditional statistical methods, and they weren't working. They were either missing the failure completely, or they had too high of a false alarm rate, so people weren't even paying attention, and it was useless. They partnered with us about 1.5 years ago, and using deep learning, we were able to give them a 93% detection accuracy with a 2-month lead time and a 5% false alarm rate. This predictive maintenance solution is saving their customers $300,000 per well per year. Very successful. Dow Chemical, I saw that there were a couple in the crowd. So they are using our GPUs to simulate chemical compounds. So in the past, it would take them 100 seconds per compound per node. So in a day, that's what, a couple thousand compounds maybe? They ported their code to the GPU, and using the DGX1, they're now able to do 3 million per day. Very high speed up. Fermilab is using our GPUs to help detect neutrinos, which are very difficult because, as you may know, they don't interact with anything, so they're hard to detect. And we're having a lot of success over there with Fermilab. Avitas is using our edge GPUs in drones to go fly around and do automatic visual inspection. Got another visual inspection use case with Penn State and University of Toronto. So they're taking really high-def pictures of the moon, and they're automatically classifying and identifying both old craters and new craters that are forming on the moon. Believe it or not, the moon has a lot of craters. It's one of those things, like the closer you zoom in, the more craters you see. So there's a lot of data here, a lot of numbers to crunch through. So they're using our GPUs for that. Kind of already hit on quantum chromodynamics. Lawrence Livermore is using it. And they got a 10x speed up over previous generations. So moving from Pascal to Volta, we don't even want to talk about what this stuff looks like on a CPU. They got a 10x speed up. LIGO. I don't know if y'all remember the gravitational waves that were detected a couple years ago. We had a really big part in that because before they were collecting all this data, of course, and it was taking them a long time to process that data. So they'd collect data, and then like a month later, they'd actually be able to use it and analyze it. Well, once they ported their code to GPUs, they got 100x faster, giving them near real-time capabilities to kind of react whenever the hints of a gravitational wave was coming in. So a very successful project that we had a big hand in there. Another visual inspection use case by Audi trying to identify miniature cracks. If you notice, we've got a lot of visual inspection use cases because computer vision is essentially a solved problem, and there are so many tools built around the GPU for doing computer vision that it's relatively easy. We got a startup who is combining both satellite imagery with social media data to help first responders better react to crises like a wildfire or hurricanes. Then we got a mid-sized retailer called Walmart. They had a really hard problem with over 100,000 different products, 4,700 stores, giving them 500 million item-by-store combinations every week that they had a forecast for. And so they were actually one of the first companies to adopt our Rapids platform for machine learning on the GPU, mostly using cuDF. So that way they were able to interact and wrangle the data using the GPU instead of the CPU. Now, all of the companies that you just saw, all those slides, are examples of what we at NVIDIA call lighthouse accounts. They're companies that came to us with a really difficult problem that has never been solved before. And at NVIDIA, we love those problems. So if you have something that's similar in your industry, you're working on a problem, like I said, that nobody's ever solved before, that if solved, can really cause ripples in the industry. It can either be solved with deep learning or accelerating your code like CPFD. Please talk to me. This is my email address. I'm in the oil and gas space, so if it's an oil and gas problem, I'd be happy to help. If it's finance or healthcare or retail, we got guys. I'll make sure you're well connected. So if you've got a problem that you think will make a good lighthouse account for NVIDIA, we have a lot of technical resources and a lot of compute power. So let us know. Thank you.